Oh no. No, it's internal, you can't see it. Alright, so first of all, the PC is very slow. Secondly, color's really bad. But you have 3D glasses, right? Maybe that helps. Alright, so show of hands. How many of you have reached level 5 or higher? Oh, very good. Okay, so you are all on the same page. Those of you who have not reached level 5, I think you need to hurry up a little bit. Okay, so far, any questions or problems with the Jedi Academy? What's wrong with this? Installation failed. This is terrible. The color is really bad. I mean really, really bad. Sorry? Both are faulty, so it's likely to be it's terrible. Okay, it was working on Saturday, right, obviously. Okay, so sorry. I think we have no choice to bear with me. And those of you, okay, many of you have laptops, right? You can actually check out the slides on your laptop also. Very slow. Terrible. What's wrong with this thing? So heavy slow. Volume is maximum here. Okay, let's see if this works. Alright, God, it's not different. Okay, so first of all, if you have sorry about this, something is really wrong today. I think the PC is completely messed up, and also the sound is also messed up, but we'll see what we can do. So life is complicated. Today I think we just have a bad day. Those of you who have PCs, laptops with you, can you please go to the slides, okay, so you can follow. The color, as if you don't realize here, is completely wrong. It's supposed to be yellow and green. It looks red, completely red, so it's all screwed up. I think the yellow and it's kind of gone. So anyway, bear with me and try to follow along. Okay, hopefully it's still readable. Okay, so first of all, last time I checked about out of 40 something of you, 45 of you, only like 30 of you are registered for recitation and tutorial. Right. Which means the rest of you are in trouble, right? Which means that actually it doesn't matter because... Hello? Okay. So this is very common. And so... Oh. Okay. Stop. All right. So, no. Man. All right. So today someone doesn't like me. All right. So anyway, this is normal. What you do is that you fill up this survey on IVLE to try to sort this out. Okay. Two things. First of all, what happens every year is that we will basically at this point check what is the enrollment for the recitations and the DGs. It seems that recitation 1 from 1 to 2 is extremely popular. Recitation 2 and 3, 2 to 3 and 3 to 4 are quite unpopular. So very likely we'll cancel 2 and 3 and we'll move it to Thursday or something. Alright. Similarly, DG, okay, then we'll put some of you in 1 obviously. That's how it's going to work. So we'll put some of you in 1. That means 1 to 2. We will cancel 2 and very likely cancel 2 and 3, 3 and 4, and then move it to Thursday or something, or later. DG on Wednesday 1 to 3 is also extremely unpopular, so that's going to die. Okay? Questions? Yes. I don't know how you bid for it, but you're supposed to bid for 2 things, recitation and tutorial. Yeah, and DG. DG is tutorial, yeah, that's right. Okay. Hello? That is bad. Yeah. Okay, so, I'm really irritated. What? Why is all of them... They're all zeros. How does this work? Yeah, it's somewhere, but it's not here. That's all zeros. Whatever. So, all right. So, yeah. I think we just have to enjoy this for now. Okay. So today is a bad day. We'll do our best to make do with the bad day, right? Okay. So first of all, whether you are level 5, okay. And one thing is how you level 6 by accident, because the path 3 got let loose in the wild by accident, and then people are there doing stuff, okay. If those of you who are trying to do the path for lecture 3 and can't figure it out, then I think it's okay, because you're not supposed to know the stuff yet until after today, okay. So you got let loose accidentally, but from this week, actually from Friday, the paths will only open after lecture. That means the paths will open at 12. Okay. We also got open early, and then you end up doing trying to level up in my lecture. It's not a good thing. So this path, the level 3 path was, the lecture 3 path was accidentally let loose. We will not happen again. But the thing is this: you want to also moderate yourself, not to kill yourself doing this thing. Okay. So the moral story is to keep up, right? Right. But don't need to run ahead. Okay. So. One thing that I don't really want to have to deal with is people who ask about things that are going to be covered in class. Okay, because it does 2 things. First of all, if we answer questions that will be covered later on in class, then except for the 2 fellas or 1 fella who wants to know this stuff, the rest of the people have no clue. Okay, number 1. Number 2 is that the people who are kind of, doing the normal thing get all kind of jittery and they get kind of worried. So I want to keep the stress level reasonably low. We want to be low anyway, but just to keep it from hitting the roof. Okay. Now the textbooks should be optional, because actually it's free, right? But generally speaking, if you come to class, you pay attention, you do your work properly, you should need to refer to textbook. But there's some people though who need to read textbooks, and you can read that. Okay. Now the thing we said this last week. Hey, this is actually. Where's my screen? Why is... Wait. Is there a screen... Hello. Okay, it's back. All right. Okay, so today is a very bad day. I have a lot of trouble, and I don't understand why, but how come my word is in the wooden thing on top? Okay, so okay, we make do. Okay, somehow something is missing and gone. The screen seems to be missing, which is why my word isn't or too high. Okay, but anyway, before you, okay, you know, right? Before you submit, I mean, when you submit, right? Press click submit, right? There's this thing that pops out, right? And says, please be sure, right? Can you please check before you click on the thing? Okay, so okay, for the first 1 or 2 missions, we will be liberally, well, we have no choice. We have been quite liberally unsubmitting your work because we screwed up, right? But we will try, okay, we will be more strict. I give my tutors more strict instructions to be more strict, okay? So essentially, if you submit randomly, you will get graded, alright? So please don't be so trigger happy, okay? And we're so eager to level up. Okay, make sure you know what you're doing before you press submit, okay? I already said last week, but you know, it happens, right? Okay, so 24-hour grading has its drawbacks. Basically, it's kind of stressful for the tutors. And sometimes we don't get it all, sometimes the tutors don't get it right completely. And also, we are now, okay, you have to understand that except for Zihan and Patrick, okay, most of the tutors are new, right? So we need 1 or 2 weeks to kind of get the new tutors actually up to speed and get this thing sorted out. So there may be some seeding bugs, which is that you may get your things graded, you know, they may be completely right. Okay, what happens is that okay, right now it's a bit random because you don't have any tutor assigned yet, right? But within the next week or so, each of you will have a tutor. So we'll probably match 6 students, 1 tutor. And for the rest of the semester, this tutor will be in charge of grading all your assignments. Okay, now random people are grading your assignment. Whoever's free, right? They're competing among themselves, a little game there. And the thing here is that the senior tutors, myself, Zihan, Patrick, and also Caleb Chow, who is actually graduated, we are looking. They'll be like roaming around, checking on the grading to make sure that everything's in order. So there may be some changes. Basically, if you are given too few points or too many points, things may change a little bit. But I hope that you understand this is a problem of speed, right? If we have a lot of time to grade, then we can all sit down and discuss, okay, how do you grade this, -2, -1, and then we can be consistent. Now that the people are running around, running parallel, it's a bit hard to control. But nevertheless, we try to be fair to ensure that the grading will be fair. Okay, so your grades, may be readjusted along the way. And this is just the trade-off that we make. Question? No, right? And obviously, you can argue with tutor over the feeds, more points, less points, whatever. And I'll be moderator. Okay, so this shouldn't be a problem, but just notice. Okay, then there have been some seeding problems. Some people get 404, right? Whatever. The reason is because we upgraded the system quite significantly since last year. It's quite serious, right? Okay, if you look at the JRCI system, it's actually quite serious business. And so if you used everything we had last year, of course, no bugs. But it turns out that Zihan ran a little bit. Well, a little bit is an understatement. He just went way out, and then basically the whole system is quite cool. But it's really quite a serious. It's a seriously sophisticated system. So, and I'm quite happy right now with the level of bugs. Actually, it's relatively low. Okay, but like last year, we have some teething problems at the beginning. Hopefully, within the next 2 weeks, everything will be sorted out. So hopefully, you all are more patient with us and more forgiving. I think that anybody who posts any bugs or problems, most of your queries or problems have been resolved quite quickly, right? Anybody want to complain? All quite okay, right? All right, good. So these are only teething problems that we will face for another week or so. Should be fine after that. Okay, paths. Let's talk about the paths. So the paths, okay. The paths are meant as exercises to help you better understand the material that is covered in lecture. It's not supposed to release before lecture. And the thing that I want, and the truth is that the path is not graded. I mean, it's not a graded thing, right? You get some bonus for some experience for doing it, but it's not meant to assess, how smart you are, right? It's just meant to help you learn the material. Some of you guys don't understand this. This means tikam means what? Anybody? No, it's not paying excuse. Huh? Trial and error. Okay, very good. So, it turns out, not just we can see, it turns out I can see everything you do there. Okay, I have got some students who have got 35 or 50 different tries. And I click on them and I see, bam, one whole page. So obviously the fella is adding one parenthesis, enter, no, wrong. Adding two parentheses, enter, wrong. So the paths actually, because you cannot fail, right? If MCQ 4 choices confirm after 4 times, you get it right. If not, you have something wrong, right? Okay, so the moral of the story is this. Please do not go and just go through motion in the path. It means basically, you know that you pretty much cannot fail, right? So you just try every single one, enter, try every single one, enter, until it's green. Good, go, proceed. Then you can continue, right? Okay, now, please, do yourselves a favor. Do yourself a favor. Use the path to do learning, okay? And the funny thing is this, it's not funny, but it turns out not just me, me and the tutors, we were actually looking at what the heck you're doing, No, there's a reason for this, right? Because basically for us to ensure you learn the stuff, you must know where you get stuck and where you go wrong, right? So I will be basically checking the path, okay? The next time I see somebody who tries 45 times or 50 times, you will be sure to get a nasty note from me. I'll go, are you okay, Alright, so no. So I just not to give you unnecessary pressure, okay? But my point here is, try not to anyhow whack. So you try something, and then you see it fails, you think about why it fails, okay? And then, and you can always ask questions on the forum, send email to your tutor, whatever. But my point is, the paths are there for a reason. Please use it to learn well. They're quite interesting, right? Okay, so the paths for lecture 1 and 2 are really quite easy. Lecture 3 is not so simple, right? Alright, it's a little bit more challenging. 4 will be okay. Alright, so anyway, the other thing is this. Later on, your two tutors on top, Joe and Zichun, will be helping me give out stickers. So please collect them after lecture. Okay, so means they will be having a station outside whereby you will go and basically collect from them. They will be issuing you some indemnity forms during the break. Okay, so this is important. Let me just highlight again that it's kind of bad, but alright, so I think this class is tough, right? And those of you who are level 5 are quite on target. Those who are less than level 5, basically it's something that you need to work on, because right now it's really rather easy. This is only the warm-up, right? And let me explain something about why level 5. Because it turns out that the maximum grade is higher than 35. But if you reach level 35, you have full grade. For the homework portion of this class, you will have maximized the grade. Alright. And it turns out the way it works is that they use the 7 problem sets, which corresponds to 7 chapters. Right. Obviously, each chapter will be how many points? 5 points. Okay. So if you kind of clear the first chapter or first problem set, you will get level 5 and so forth. So roughly that's how you see a progression. And the first problem set, or rather the first 3 questions, is relatively simple. Okay. Moving forward, it's going to get harder and harder. Okay. So I'm not trying to scare you, but if those of you who find after the end of this week that this class is too fast, okay, the stress of the academy is killing you, you may consider, switching to 1010, because, the whole point here is not to be fast. The whole point here is to find learning that is at the right pace. Okay. Okay, so now we will start on the real stuff. Okay, so today we will cover this thing, which is the real stuff. Okay, first of all, anybody tried this? This is the last question we stopped at. Infinite loop. Why? Okay, let's take a look. Okay, so full 5, right? Full 5 is what? Full 5 it's actually, if you look at the definition, let's see, definition is this, right? Lambda full x is what? Star x full x minus 1. So full 5 is what? Times full 4, right? Correct? Full 4 is what? Times full 3, right? Okay? So you do this, you open up here, and then you do this, right? Hey, but multiply is 0, right? So you all know that anything that multiply is 0, right? So answer is 0, right? Why not 0? No, but you know, you all know, even kids know that you multiply anything by 0, it is 0. So if you multiply anything out, there's a 0 inside there, the answer is 0. Well, it turns out that this thing continues going on, right? Because it turns out that your computers will follow your orders precisely. And in this program, what you've done is you've asked this computer to keep going on, and it never gets ordered to stop. Okay, so this thing will end up being, it's not a loop even, it's just hangs up. Right? Because it keeps going on to negative infinity. So this is important to understand. Okay, so the whole class, the whole course is really about managing complexity. Okay? And obviously the whole point is to solve problems. Okay? So the color is terrible, but the slides look much better than that. You are seeing the slides? Okay, so those of you who see this kind of blur, you can look in front and see the color, it's kind of pretty. Okay? So just to know that it looks better than this. Alright, so the point is this, you are trying to solve problems, okay, and find solutions to them. So there are two things. There are this thing called primitives, which are the things you work with, right, and this thing called abstractions. Okay, so essentially, abstractions are these things that you invent to make the task easier, right? Oops. So the question today we're going to ask and answer is the following. What makes for good abstraction? Okay, number one. Okay, it's kind of common sense, actually. Sadly, it's sad to say it's kind of common sense. First of all, the abstraction must make it easier for you to think about the task and subtask. Okay, so for example, if you want to build a house, right? Obviously, okay, Singapore is a bit different. Singapore, you prefabricate, you put it together like jigsaw puzzle. But let's say you're in US, okay, or New Zealand, right? Where you come from, Richard? New Zealand, right? Christchurch. Oh, okay. It's a place whereby the earthquake hit, right? All right. So I believe maybe they build houses with bricks or something. So one thing you can think of a house as a bunch of bricks, but that's kind of nasty, right? So what typically people do is they think of a house in terms of rooms, okay, and then they think of the rooms in terms of how to build a room with bricks. So that's essentially the general principle here. It's called divide and conquer. You take a big problem, you break it into smaller problems, right? Okay, and similarly, you have the same concept, right? In the same way, you can think of a house in terms of bricks. Instead of thinking about programs in terms of primitives, okay, you can think of it in terms of procedures, okay, kind of basically defined using primitives. Okay, so the next thing about abstractions is that you can make programs easier to understand. Now, this course is a little bit different because you will write only small little things that, frankly, only you and your tutor read. Okay, but frankly, if your tutor cannot read your code, okay, he's not be kind. So the point here is that it's important to write good code so people understand what the heck's going on. Alright, so for example, look at this code. So it says hypotenuse AB is the square root sum of squares AB. Alright, then you define sum of squares AB, xy to be the sum of square x and square y. And finally, you define square x to be star xx. Okay? Are we all familiar? Okay, this is simple enough. Alright, if any time you are... Okay, so, like I said, the pace of this class will start accelerating. And the way to moderate the pace is to ask questions. Okay? Now, next, look at this answer here. This is the answer. Define hypotenuse AB. Star the thing. So, the top one is probably a bit more verbal, right? But it's also more clear. Okay. Now, important. Okay. Some people have submitted code. There's one long line. In the missions, right? So can you please? Okay. There is a certain scheme style in writing and in formatting code. Okay. So after a while, your code should all look look and feel the same way. Okay, one whole line. Okay, it works. Strangely enough, it may be obscure, but it works. You try to code one long line, it actually works. Okay, but I will not be too pleased. The tutor will be completely upset. Okay, so you learn the thing, and then Zitun, I think he's posted some dummy's guide to formatting scheme code, right? Actually, okay, you don't have to learn that. You don't have to learn that, right? Actually, it turns out that you use Docker scheme, you tap or something, you indent properly for you. So you don't have to think too hard. Okay, just use those features. Okay, and then the point now is that you need to align things that are kind of aligned. Okay, I mean it's kind of obvious, right? Because if this is a plus and there's two pieces here, you align it. It makes it easier to see that hey, these two pieces are going to be added together, right? Okay, so it's not common sense stuff. Okay, after a while you should be used to this, but the earlier you learn this, the better. Okay, also understand the style helps you appreciate code faster. Okay, next, this abstraction should capture common patterns, and this is something that we'll come back to quite a few times during the semester. So one example you saw, remember the picture language, whereby you try to do this, this is called, what is this called? Make cross, right? Okay, so you can't see it very clearly, but here you have r cross dd. What you can do is you can actually replace r cross dd with pig, right? So essentially you are replacing, the common parts and creating a procedure. So you are actually looking at the patterns, okay, and abstracting the pattern out. Okay, this allows you to do code reuse, right? Okay, next. So I was saying code reuse. So for example, okay, a procedure called square, which of course square something, can be used in sum of squares. Okay, but it can also be used to compute the area of a circle. Okay, now it's an example. Suppose you have pi 3.14159. Okay, and then you can compute circle area from radius r using this formula, right? Multiply pi by square of r. Okay, it turns out you can also compute the area from a diameter, right? And what you can do, if you look at the second example, is that you call the first procedure, okay, and you just pass in the appropriate argument. So here you can reuse procedures to define more complicated procedures. Okay, this is a very important idea, okay, and one important idea of abstraction is actually this idea of information hiding. Okay, basically, if you remember correctly, if you remember from the first lecture, okay, much of what we do is about managing complexity. Okay, it turns out that managing complexity also involves hiding stuff that you don't need to see so that you get confused. Okay, so for example, if you look at the water molecule, this is terrible here, but you can either look at it as H2O, okay, or sometimes, for more sophisticated analysis, you cannot actually deal with this using this model, so you need more complicated models. Okay, another thing I remember we are doing it already is that we have actually hidden away I kind of told you in class how stereograms are generated, right? But you don't have to know, right? You just have to call stereogram and then it coughs out the thing. Alright, so this again hides the details of how the thing is done. Okay, so what abstractions do is that oftentimes it separates, okay, the specification from implementation. Recap, So essentially, procedure abstraction means that you want to take a bunch of operations or a bunch of things that you do and wrap it into a black box, so that you don't have to care you don't have to care how the box does it. All you need to know is what the box does. Okay, so the same principle is that you don't need to know how you build a car to drive it. Okay, so procedure abstraction separates specification from implementation, right? And specification is the what it does. Okay, so essentially a procedure will specify, there will be some instructions specifying, okay, this procedure does the following. Okay, and you should be able, if the procedure is written properly, you should be able to use it without knowing how it is done inside. Okay, that is the implementation. Alright. Okay, this is a very basic concept. After a while, you should be second nature. Okay, example. Suppose you have square x, which is star xx. Okay, and then it turns out you can also define square in a very obscure way, right? Means you can define square as the the exponential of the double of the log of x. Okay, And double x you can define as plus xx. Okay? So my point here is that it turns out that if you use either of these two procedures, you should get the same answer, which is the square of x. Okay, one is nastier than the other, but they are both the same thing. Okay, then the question is why am I doing this? Why do I have two different implementations of the same thing? Isn't one enough? Okay, so this is a question that I leave for you to think about. Those of you who feel inspired can post something on the forum, and then we can discuss. Okay, but the truth is that you have procedures, okay, and the procedures allow you to implement the same thing in different ways. Okay. Now, another thing about abstractions is that it should hopefully make debugging. Okay, you all know debugging is to fix errors, right? Okay. So what's the name, sir? The man behind, the guy in the black. Huh? Eugene Chong, is it? Who? You are Chong, and you are Ang. Tired, ah? I have a copy now. Eugene. So the point is this: to have me know you by name faster, you sleep. Very good. Okay, Richard already well known, so you can sleep already. The rest of you who want to be the girls, unfortunately, can escape because so few of you, I don't know your name. Okay, but the guys, okay, I'll take a bit of time. All right, so the question is this: look at this piece of code. Other than the fact that it's horrible and purple, where's the bug? Where? Okay, for fast, y'all. Even though the color is horrible, you can see. Okay, so how do you find the bug, right? Basically, you will go inside there, you say, okay, hypotenuse is the square root of sum of squares. Is this correct? Correct, okay. You keep going down, and then you see a square x is plus xx. You say, not quite right. So here's the bug, right? Now, suppose if this, another one that looks like this, okay, where's the bug? Yeah, but you see, the point now is that, okay, this one is much harder to check, right, to some extent. Right, whereas if you write it out, in more verbose way, okay, what it does allow you to do is it allows you to check each part for correctness one at a time. Okay, here is a bit messed up, and here I made a little trick where I sort the signs. It looks kind of the same, but it's not quite, so it's much harder to see this. Okay, so hopefully if you have good abstractions, you will help debugging, right? And the truth is this, the truth is that writing code doesn't take a long time, You realize that most of the time is wasted finding bugs. Okay, if you're and you will think that the better coder you are, the faster you debug. Yes and no. Actually, the truth is not so simple, because the better a coder you become, the nastier a bug get. Okay, it will turn out that way. This is that if you're a good coder, you will just not make the simple mistakes. You make these horrible mistakes that are hard to debug. So to some extent, as you get better and better, your time spent coding and the time spent debugging is kind of proportional. Okay. Obviously, it also depends on what kind of code you write. Right? As you get better, you write more complex code. Okay, so variable scope. Now, suppose I do define x10. Right. Okay, and then I do define square x star xx. Okay, I'll follow. And then, square x is star xx, double x is plus xx, and then add xy will be plus yx. Okay, then I do square 20. Okay. Sorry? Yeah, so it's space. So next I do square x. Then look, I ask you, which x? Huh? Why not this x? Not x. Okay. Add x5. Okay. Which 5 is which is? Okay. So the problem is that, okay, if you look at this thing, right, there's a lot of this x and y, and the question now is what is what? Okay. So let's take a look. Okay. Now, so it turns out that a procedure, okay, it will bind what you call the formal parameters, which are the things here that follows the name. Okay, so this is the formal parameter, okay, and it will bind the formal parameters in the body. Okay, so essentially what it says is this: the formal parameters, which are this stuff that follows after the name, okay, they are visible only within the body. Okay, they're not visible outside the body. Okay, and then the parameters that are formal parameters and are bound are called bound variables. And the region within which this variable is visible is called a scope of the variable. Okay, this is not unique to Scheme. All languages have this kind of concept. Okay, but Scheme tells you what is visible where, right? Okay, and any variable that's not bound obviously is free. Okay, so that's simple. This is a simple definition. So suppose I do define x10, and I define square x sasa. Okay. Then in this definition, basically your x, okay, you cannot see this very clearly, but it says x is bound, it's green, okay, because x is a parameter for square. Okay, here, double x, again, x is bound. Add xy, y, what is this? So it turns out that y is bound, okay, and then inside the body you have x, right? Okay, I say again, I define x, define add xy. In the body, there are two things, right? There's y, there's x, right? X is bound, okay, which means that, y is bound, which means that, where's my, so this y, can you see my arrow? Okay, it's a pink little thing. Okay, this y is bound to this y. This x is, however, free, So with free, it means that it will refer to x that is outside the scope, so it will be here. Okay, so the question, is the plus in add x, is it bound or is it free? Free, quite easy. Okay. Now next, suppose you have pi 3.14159, okay, and then now for no reason inside here I also define pi to be 2/7. Can you see now? So there's a pi outside, there's a pi inside, and then now I call pi. Which pi is pi? Okay, so essentially this pi will refer to the inside pi, because inside this scope here, the pi is this. Okay, so this pi will actually hide the outside pi, and if you get rid of this, if you delete this pi will then become the outside pi. Okay? Yes? Good question. Can you not? You think? No lah. If you bound something that is using different name, okay But if you are bounded using the same name, sorry cannot see already. Okay. So basically over here, what you've done is you've actually ridden the outside pi. So for within the body of this procedure, this is what happens. So you can't see anymore. Sorry. So we must try to name things properly. Okay? Alright, and this thing, by now you should figure it out, this semicolon thing is what you call a comment character. Yes. The question is it correct to say that it's going to find the definition closest to the parenthesis? It is semi-correct to say that. It is not entirely accurate, but in a few weeks after the midterm break, we will tell you exactly what happens. Okay. So I would basically say that you want to hold this question for a while. Right now, it's really quite simple. Just know that you have procedures. Inside procedures is a scope. Okay. Anything you define inside there will be visible only inside there. Okay, anything else that's not inside there will be checked outside. Then the same rules apply recursively. Okay, but like I said, in a few weeks, we do some really gross things to show you exactly how this thing goes up and down or whatever. Okay, but for now we will not introduce that yet, because life is already interesting enough. Okay, if I do that today, probably half of you will drop the class. So I'll keep that for a while. Okay, we will do this. It's called environment model. Okay, if you're really very interested to know this, you can read up SICP. Okay, and read the chapter, which not the chapter, is section called the environment model. Okay, but if you freak out, you keep it to yourself first, and then we talk about it in a few weeks. Okay, so but basically, I think we just for now remember the simple rules. Okay, whereby it's just within the body. Okay, good questions. Excellent. Okay, so then oftentimes the code have this kind of block structure. And exactly like what you said, you have a procedure, You're a procedure in the procedure. Okay? So this thing is known as a local procedure. That means anything outside here cannot see this sum of squares. Sum of squares is visible only within the body of hypotenuse. Okay? Now, so the variables a and b, okay, over here, in sum of squares, a and b, they are what? They refer to these two. Okay, they will refer to the two formal parameters of this hypotenuse. Okay. Now, so the whole point of this block structure is that it allows you to hide details. Right? It means sum of squares is something you may not care about if you're outside hypotenuse. The guy only cares that you compute hypotenuse. He doesn't care how you compute it, and he doesn't care that there's extra procedures floating around. Okay. Now, next thing I want to talk about quickly is conditionals. I think you saw some of that last week. Okay. So, conditionals are things that have cases. If A is this, you do this. If A is the other thing, you do something else. So one simple example is this absolute function. Absolute function does the following. It takes a number, okay, and if it's negative, it flips it over, flips the thing positive. Essentially, you want the magnitude of that thing. Right, so absolute ABS is defined as x if x is positive, okay, and negative x if x is negative. So there are two ways to define that, okay, here. One is you can use if, okay, basically if x is less than 0, you will return minus x. Okay, the other one is to use condition, which has a similar kind of structure. I'll explain it in a while. Okay, so first of all, there's a defined special form, remember we explained last week, whereby you evaluate expression, okay, get a value, and then you bind it to the symbol. Okay. Now the con is also a special form. Okay. The con has the following form. I think some of you have seen it in the past already. Where you have this P is a predicate. Okay, there's a whole bunch of predicates which are kind of expressions that will evaluate to either true or false. Okay, and the E's are the consequent expressions. Okay, so what happens in con is that you evaluate P1. If P1 is true, you return E1. Okay, if it's false, you will go down to P2 and evaluate P2. If P2 is true, you will return E1, E2, and so on and so forth until the end. And then you can also, at the end, you can have an else, whereby it's like, I give up and you just return this thing. Right? So this is a very common thing you do. Okay. Quick question. I tell you define is a special form, and I tell you the con is a special form. What exactly is a special form? Do you know? Not really. Okay. So the whole point of this is the following. If you remember scheme expressions, right? The typical way to evaluate them is do what? You eval, and you apply. That means you evaluate every single piece, every single sub-expression. Okay, this parenthesis thing is known as a combination, right? The parenthesis thing. And then the combination consists typically of an operator plus some arguments, right? So the typical way of evaluating a combination is that you evaluate every single piece, okay, and then you apply the operator onto the pieces, right? In special forms, you don't do that, okay? Now, you see, if you define is not a special form, then you have to evaluate symbol, you evaluate expression, everything. But you don't do that, right? In define, what happens is you just evaluate the expression, and then you bind to the symbol. The symbol is never evaluated, okay? Now, in the con, there are many pieces, no? There are many pieces. That means there's con, there's piece 1, piece 2, piece 3, and piece 4. It turns out that you don't evaluate everything. You evaluate one piece, and how you evaluate this piece? You evaluate the P1. If it's true, you return E1. So it is possible that the remaining stuff don't actually get evaluated at all. Okay, whereas in a typical non-special form procedure application, you evaluate everything. Okay, so I say again, special form are this kinds of things or entities for which the evaluation follows some special rules. It's not your typical eval apply. Okay. Again, we will come back to this, but let me just highlight this for now. Predicates. Okay, essentially, these simple things like greater than, less than, this is less. Okay, so 5 less than 3, true, false? False. Okay, so here I also introduce you to this thing called true and false. So true is, what is it called? Hash T. False will be the hash f. What's this called? Hex, whatever. Okay, I can't recall. But this symbol, this little thing like your apartment number. Okay, next thing. 6 greater than 3, true or false? True, so you have passed kindergarten and can count. Very good. Okay, so you have conversation operators. So it turns out that you may want to check for multiple things. Okay, and who here knows the AND OR? You don't know, right? AND means what? AND means that everything, not just both, not both. AND can take many pieces. Okay, so AND can take a few pieces. AND something is true if every piece is true. Okay, any piece is false, it is false. So this one, true or false? Why is it false? 2 not got 1, huh? This one? Then this? Okay, the two things you need to learn are, AND means everything must be true for the whole thing to be true. OR means what? Anything, any one of the things is true. Okay, simple, huh? So this answer will be, I also don't know yet. I don't know what expert also. Okay, but okay. Then the last thing you need to know is this thing called NOT. Okay, NOT is true. Okay, NOT. Okay, AND and OR can take multiple arguments. Many arguments. In fact, as many as you can type. Okay, NOT will only take one argument. So what NOT will do is that you invert the truth value of that argument. So if this thing, if you do NOT greater than yx, you're effectively saying smaller equals to y. Okay, because NOT will invert the value of that argument. Okay, so if special form, it turns out that if is active synthetic sugar for con. Okay, if actually means con, predicate, consequent, else, alternative. Okay, so that means you don't actually need if. Okay, so why do you have if? Because it makes programming easier, it's more natural, right? Con is a bit clunky, okay, in terms of typing out. So if is much more natural kind of a form. So again, if is some form of synthetic sugar for con. Okay, it makes code reading easier. And if is a very common kind of thing you need to do, right? To check before you decide between two things. Yes. Consequent one bracket. What do you mean? Which link? Second up is yes. Yeah? Then how, right? No, that's not true. It's not true. There's a thing called begin. If you want to do a lot of crap there, you can. You just add a thing called begin and then you can have lots of lines, so it's okay. So the question, Jen, right? Yeah, Jen. Okay, so basically the question that Jen asked is it true that you can have one bracket here? The answer is yes. And if you only one bracket is very nasty, right? Because it seems like allow, okay, when you do that. But it turns out that there's this thing called begin, which we will talk about in a few. Right now, okay, very kind, you're not required to do a lot of crap there. So it's not very easy, okay? But later on, if you want to do a lot of stuff, there's this thing called begin, you can stick it in there and then you can do a lot of stuff. Okay, so it's not a problem. It's not a problem. This is a small thing, right? So this question is not a huge concern. Okay, but good question anyway. Okay, another thing is this, very important. Hang, right? Hang. Okay, she posted this quote. I'm not trying to embarrass her, but the question was, why was it wrong? Okay, the reason, okay, now as you're young, the thing to realize is that parentheses means something. So don't suka put parentheses now. I mean, it's not, okay, scheme, okay, if scheme, okay, in scheme, I never explained to you. You want to use the minimum amount of parentheses because more actually confuses you and typically you don't know what you're doing. Okay, so remember, every time you do parentheses, open and close, you are doing what? You are evaluating something, you're doing a function call, actually, some sort. Okay, so you cannot happily, put define procedure and then, open parentheses something, then open parentheses something, just because it looks kind of neat. Okay, so what that does is generate bugs. Okay, so it's important for you to go and figure out when the parentheses happen and actually use only the right number of parentheses. Okay, again, this should be quite clear after a while, but you must be careful about parentheses. So it's good that Jen asked how many parentheses, only one. Okay, So the thing to note about if is the following. Exactly one of the consequent or the alternative is evaluated, never both. Okay, and whichever is evaluated depends on the predicate, obviously. Okay, let's quickly do a taxi example. Okay, sorry, I must admit I haven't gone to check taxi prices for a while. I don't take taxis, but it used to be this amount, and now it's very confusing because now you have different kinds of taxis. You got the limos and then the small ones. It's all kinds of random stuff. So it's very hard to. In the past, it's good. In the past, it's all same price. So let's assume for now that this is a. Also, PTC just recently, allowed what things to the bus prices increase. Right? So things are changing all the time. So for now, just assume that it's 280 for the first kilometer. Okay, and every if you can't read properly, 385 meters up to 10 kilometers is 20 cents. And every 330 meters after that is 20 cents. Okay, so the whole point here is that you're trying to compute for a taxi driver how much it costs in fares. Okay, so the problem is obviously the following: to write a scheme procedure that will compute taxi fare. Okay, so how do you go about doing this? Right. So our whole goal in this class is to write programs to solve problems. So this is the problem. Okay, so how do we start? How? Panic first. Okay, so first of all, we must try to understand what the problem is about. Okay, so first of all, you must go and formulate a problem. Ask yourself, what the heck am I trying to do? Okay, so, and what is this procedure going to do? Essentially, it is a name. Okay, so, there are some of you, all the NOI people, programmers, can you please try to give some meaning to your names? It's not all X and Y, it's very irritating. Okay, so basically name your procedure something, okay, and try not to use foo. Although, okay, I must say I'm quite bad. I use a lot of foo-bar here for examples in class, because foo-bar is very in fashion for computer scientists. Okay, but in your work, can you try not to do this? Okay, call this like taxi fare or something. Okay, so what happens in taxi fare is the following. You must model the problem. You shove in the distance, right, and out pops the fare, right? This is the idea. Simple, huh? Alright. Okay, for some of you, this is a bit slow, but bear with me, things will speed up. Okay, so the question is, you ask yourself a few things. First of all, what data do I need to solve this problem? These things will go into the arguments for the procedure. And where would you get it? Whether the things you need needs to be passed in as arguments, or whether you need to compute yourself. Okay, this is a very simple example. Later on in life, when you have more sophisticated questions, then you have harder questions to solve. Okay, next. The results should also be unambiguous, because you look at this procedure, it's like a function. Function is a what? One-to-one. Could be something to one. Okay, could be many one-to-one, whatever. So, but the whole point is always a to-one mapping, right? You don't have randomized kind of thing. It's kind of random. Okay. So the question is this. You also ask yourself, this is a simple procedural abstraction. You also ask yourself, would there be other abstractions that are useful? Okay, and then ask this carefully. Okay, so now the first question is this: how can the result be computed from the data? Okay, so the first thing this is quite a simple example. So to be honest, you can just cough out the numbers, the whole code. But sometimes it may be complicated, and one approach is to try simple examples. Okay, do something small problem, see how it works. Okay, and then you try to figure out step by step how to do this better for bigger problems, and then you write down and refine the whole algorithm. Okay, so first of all, let's look at how we solve this problem. Okay, what do you call procedure? We already said already. This is going to be called taxi fare. Okay, this is ugly purple. Okay, what kind of data do you need? You only need the what? A distance, right? Okay, and then where do you get the data? Basically, input right? You actually use a procedure argument. People tell you the distance and you copy out. Okay, the result is a fare. Very simple. Okay, so the first thing to do is you look at the problem. Okay, how would you solve a problem? Suppose the distance is 800 meters. Then obviously you know that less than 1 kilometer is 280 flat rate. Now suppose it's 330 meters. 3,300 meters. Then what you do is this: what? You go and take 280, you round up 230, 2300, sorry, divided by 385, multiplied by 20 cents. Okay, and suppose it's 14,500 meters. Then essentially you have more steps. Okay, so this is the answer as defined by the earlier problem. So how do you write the code? So essentially you know that if distance is less than 1,000, the answer is 280. Suppose the distance is between 1,000 and 10,000. Sorry, it's not very clear. You have to squint a bit. Then the fare is 280 plus 20 cents times the roundup of the distance minus 1,000 divided by 385, right? Okay, it's really blur. Okay, finally, if the distance is greater than 10,000, right, then you have 760. Okay, 760 is what? 760 is the fare for 10,000 meters, right? Okay, and then you multiply 20 cents by the roundup of this distance minus 10,000 divided by 330. Okay, note that in scheme there's this thing called ceiling, which actually rounds up to the nearest integer. Okay, so this is the distance. Okay, and next. Okay, once you've written out this whole thing, you can convert into code. Okay, so what this code tells you, use the con. Alright, so if the distance is less than 1,000, the answer is 280. Okay, if distance is less than 10,000, okay, then it's this thing. Why do I not have the greater than 1,000? Because if it's less than 10,000, already taken care of, right? So you know that by the time it falls through this thing, this situation is already the second situation, which is that it is greater than 1,000. Okay? And similarly, after this less than 10,000, we know that once it falls out of this part here will be more than 10,000. Okay? So this is simple. So can we improve the solution? Is this good? Why not? Yeah, it's kind of nasty, okay. So the important thing to understand in writing code is to basically think about coping with change, right? Suppose, if the fare get increased to 320, okay, then what happens? And what happens if 385 get increased to 400? It's quite nasty. It means you need to go through the whole code and figure out what changed what. It's kind of pain in the butt. Okay, so the key takeaway here is that you want to avoid magic numbers. Okay, one quick thing. This is how you have printed the slides. So I would recommend you all print slides reverse video. So otherwise the full printer gets killed because it's all black. Okay, so you can do that. Okay, you can click on this thing to reverse the color. Alright, and number two is that my slides will change. Because typically the night before I give a lecture, I will go through the slides and they'll make some minor amendments. Mostly okay. You can print earlier than that. Okay, but just note that the slides you see may not be completely the same. Today's color is off, not my fault because of the projection, but typically the same color. Okay, so alright. So back to this thing. It's terrible to make this hard-coded constants. Okay, in the code because it's very hard to change. Right. So the general idea is use abstraction to hide them, and the abstraction you use is basically naming. Okay, so very simple. Now, so let's look at version 2 of the code. Just now, when you look at earlier code, right, I put in all the numbers. Now what I've done is this. At the bottom here, I have defined all the variables. Stage 1 is 1,000. Stage 2 is 10,000. Okay, starting fare is 280, so on and so forth. And then instead of all the numbers, I've actually put in the variables on top. Okay, it's quite simple. Now, interesting thing to note is this. Here, what I've done is this. Okay, just now I put 760, right? Correct? Remember? The funny thing is that it's actually not, that number there is actually not a real number, right? The number is really the fare of 10,000, right? Okay, and I have no choice but to do a recursive call because if I put any number here, it's almost certainly wrong, right? Because upstairs I change things, the whole thing will change. So instead of doing that, I'm actually making a recursive call, which means that this procedure is calling itself. Okay? So this is kind of interesting example. Simple but interesting. Okay, okay. At this point, I think I want to highlight one very important thing. Okay? It is this concept called wishful thinking. Okay? I'll just introduce today. You probably can't appreciate it completely. Hopefully, by the end of the semester, you will actually understand this. Okay, so what exactly is this? It's a very simple idea. So, in writing programs, there are two ways to do it. There's what you call the bottom-up approach and what you call the top-down approach. Okay, wishful thinking is essentially a top-down approach, right? So essentially, you just write the code as if you have what you need. Okay, later on we'll show you the example. Okay, here's the example. Now, suppose you need to write a procedure to compute hypotenuse. Okay, this is a triangle. So how do you do this? Okay, obviously you can go to the math textbook, look at the formula, and just put in the formula. Well, another way of doing it is the following. You can say, okay, the hypotenuse of AB is the square root of the sum of squares A and B. Now, note that at this point in time, when you're writing this code, okay, square root, it turns out exists. Square root is actually a predefined procedure, so it's okay. It's somewhere inside there, it runs, it's okay. But then suddenly you just put in this thing called sum of squares A and B. Okay? At this point in time, sum of squares A and B doesn't exist. It's okay. Alright, so you just type in, okay? Then now you have already finished defining hypotenuse. Okay, now what you realize, however, here is that sum of squares A and B doesn't exist. Then you say, okay, what the heck is that? So then you go, okay, define sum of squares xy to be the sum of square x and square y. Okay, which is true, right? But at this point in time, actually square doesn't exist. Okay, so then you realize, okay, to fix this problem, I will go and define square. Okay, now it turns out that after writing all this code, right, you will find that you will actually have the running hypotenuse code. Okay, so it's very obscure because the point here is that you're writing stuff based on stuff that doesn't exist. Okay, but what you're doing here really is that you're taking a big problem. Okay, you are actually breaking it down into smaller problems. Okay, and this is known as wishful thinking. You will do a lot of this in the next X weeks. You have no choice. Okay, but right now let me just highlight to you this is what it is. Okay, and we'll probably revisit later. Okay, now we go into recursion. But before that, let me just give you a break. Okay, sleeping. Okay. Actually, I want to show you videos, but I don't think it's going to work though. I think it's broken. And there's no sound too, man. This is really broken. Okay, let's see if I can get this to work. Okay, the sound sort of works. Whoa! Sorry. Yeah. Okay. Okay. Anyhow, this one is more listen than watch.
My name is Jeff Bezos. I studied electrical engineering and computer science, graduated in 1986 from Princeton. And my current job, I'm the founder and CEO of Amazon.com. Well, the Kindle is a wireless electronic reader. We started working on it more than 3 years ago now, more than probably almost 5 years ago now. The idea is to take the key features of a physical book, capture those, and then go beyond that. The number one feature of a physical book is that it disappears while you're reading it. You're not thinking about the ink and the glue and the stitching and the paper. You're entering the author's world, and the physical object just goes away. And that's what we wanted to achieve with Kindle, to have a device so simple that it too would disappear unless you enter the author's world. Failure is an essential component of innovation and invention. If you know it's going to work, it's not an experiment. And so if you want to invent, if you want to innovate, failure is part and parcel with that. There's no escape from that. If I were to go back in time and give myself one piece of advice as an undergraduate, it would be take pride in your decisions and hard work, but not in your gifts. Celebrate your gifts. enjoy them, but don't take pride in them. Take pride in your decisions and hard work. My best memory of Princeton is finishing problem sets in partial differential equations. And my worst memory at Princeton is starting my problem sets in partial differential equations. For anybody who is starting, if anybody is their freshman week and they're starting at Princeton, I think the advice as to what to focus on is pretty simple, which is to figure out, which is not always easy, but try to figure out what you're genuinely interested in and then pursue those things. Alternative techniques might be try to figure out what you think is going to be most lucrative, and I think those techniques tend not to work. It's very, very difficult to chase after a wave. What's better is to plant yourself in the middle of something that you genuinely love and then wait for the wave to come find you.
Okay, so hopefully you have figured out what...
That just makes the video better, you guys.
Okay, this is random. Okay, so it's over. So I think if you didn't catch it, what he said is that, okay, it's very hard to... well, okay, thanks for fixing something fixed. So I have people rescuing my video. Okay, so the point here is that it's very hard to try to figure out where the wave is going to be and then try to put yourself in the wave, right? It's probably better to figure out what you care about and hope the wave hits you someday. So this guy is an engineer, obviously, Princeton engineer. He's who the heck is he? Jeff Bezos, right? Founder, CEO, Amazon.com. Okay. And funny thing is that he used to work in Wall Street. I think he used to work for D.E. Shaw, which is the hedge fund. Okay. Okay. Let me just play another video while we're at it. Okay, let's take a look at this one. This for kick.
我叫刘伟，来自北京，梦想就是成为一个一流的音乐制作人。10岁那年让我感受到了生命如此的脆弱，可能在几秒钟就会失去生命。记得那年我跟我的同学一起玩捉迷藏，不幸被电意外击倒，度过了45天的生命危险期。但恢复意识，我意识到可能永远的失去了双臂。我就哭了，问了几个问题吧，就是我怎么样吃饭。他说你得练习自己吃饭，要不然以后我们老了谁照顾你？那时候我母亲灌输我，你没有跟别人不一样，所以我现在觉得我跟别人没有任何不一样。我只觉得你们用手做的事情，我用脚做。我妈不求我有多么大的成绩，她只是要求我健健康康的好好的活着。但是对我来说，我要为他们做的，就是一定要做得很成功。来中国达人秀，我的最终目标肯定是前3，让母亲很自豪地说起他儿子。
我正在想，为什么琴凳是那样的，在钢琴前面你用脚弹钢琴？
对。
哇哦！
那你什么时候开始弹钢琴呢？
我是19岁弹的钢琴。
那刚开始学很辛苦吗？
很辛苦。
你刚开始用脚学的时候有受伤吗？你的脚？
有，磨破啊，或者抽筋之类的。
我们用手弹都磨破，不要说用脚弹。
因为我只觉得它是一个我的兴趣爱好，我觉得我想做的事情，我就要把它做下去。
好，接下来看你精彩表演。 其实没有话要说，我觉得我想让观众听你说，你怎么能匪夷所思？我们用手学钢琴都学很多年。
我觉得在我的人生中只有2条路，要么赶紧死，要么精彩的活着。没有人规定钢琴一定要用手。
我觉得，包括我自己在内，包括我们3位评委在内，包括电视机前的观众，大家看看刘伟，听听他的音乐。我觉得生活中有任何的抱怨或者不满，都应该没有。你看看一个这样的年轻人是怎样能弹动钢琴，而且是打动人心。我觉得我们都应该放弃所有的对生活的抱怨，像你说的，精彩的活下去。谢谢你。
你让我看到了达人中的达人。我觉得真正的达人是用生命在展示他的才华的，而不是一个秀什么东西这样。我很感动，我会让我的小孩看这一期你的这块节目。
谢谢你给我们带来这么美妙的音乐和这么淡定的状态，谢谢。
对于你这样的一位达人，你真的是一位达人 ，talented。我们不应该用 yes 什么这样的词，我们应该这样表示，叫祝福你，谢谢你。
在我的人生中只有2条路，要么赶紧死，要么精彩的活着。
Okay, so so those students that don't speak Chinese, I apologize, but fortunately it's from the Chinese talent show. So I mean, this is like China has talent. Let's see, it's in Chinese, right? But the whole point here is not about it's not about the Chinese parts, right? It's the fact that this fella has got no hands, right? Okay, so let me quickly summarize for those guys who don't speak Chinese. Essentially, this guy has no hands. Obviously, you can see that for yourself, right? And he plays Richard Clayderman, right? Okay. So, why am I showing you this? It's because some of you will find the next few weeks' life is going to be hard, right? And then you're here struggling trying to do this scheme program, and you ask yourself, hey man, then you think, okay, is it harder at scheme program or to play a piano with your toes? Okay, and he said something very interesting. Let me just explain to you. So he was asked by the judges, what is it that helps you, have determination to play the piano with the toes? And he said this, right? In life, for him, there were 2 paths. One was to go and die, right? The other one was to live life in a way that is as exciting as possible. Okay, and he chose the latter. Okay, so hopefully, when you guys find that it goes tough, you can go try to play the piano with your toes and feel is that tougher or doing scheme problems that is tougher, right? Okay, we need to go back to class. Are we okay? I just go back and see. Yeah. Of course, that'll be very good. Thank you very much. How do you do that? Thank you very much. Okay, I'm really confused. Okay, good. Now we have the screen working minimally. Color may still be wrong, but we'll live, and then the technicians will fix the thing later. Okay, cool. So now we will go into the real stuff for the course, pretty much recursion. And the color is still wrong, but we'll see how it goes. Okay, so first, we have this thing called factorial, which is n factorial. Essentially, factorial is what? It's a product of n all the way down to 1, right? And it turns out that you can write factorial in the following form. You can write n factorial as n multiplied by n minus 1 factorial, if n is more than 1. And you can write, and n factorial is 1 when n is 1, obviously. Okay, 0 factorial is also 1. Okay, but for now, just start with 1. Okay. Oh no. Hello? Okay. Right. So, this is the definition of factorial. Okay. And it turns out that you can write the following. You can write define factorial n. Hello? You can define factorial n to be if n is equal to 1, right? Which is what we say up there. Okay? And otherwise, it's just what? Star n by factorial n minus 1, right? Okay. So it turns out that this piece of code actually works. Okay. So if you run this code, you will actually get n factorial. Okay. Now let me just quickly go through this part. The first part here, where you have this equal n1, this is known as the terminating condition. Okay. And over here, when you call factorial again, it's known as a recursive call. Okay. So note that a procedure that calls itself is called a recursive procedure. And for Scheme, you will find almost everything is a recursive procedure. Okay. Now let's look at this example. Factorial 6. So if you look at what was defined in the earlier screen, factorial 6 becomes what? Star 6 factorial 5, right? And then you need to basically evaluate factorial 5. Okay, this becomes star 5 factorial 4. So you keep going down, you open up. Right? At some point, you reach factorial 1, right? Okay? But factorial 1, you know that it's an if statement. If n equals to 1, answer is 1. So what happens is that factorial 1 becomes 1, right? And then you end up having this thing closed. Okay? The answer, obviously, is 720. Anybody has a different answer? Oh, same, right? Very good, huh? So this is the thing. Now, the thing to note about this whole evaluation process is that there are a lot of stars, right? There are a lot of this asterisks. So it builds up, okay, to a certain point, and then it starts to close. Okay. Now this these operators that are kind of pent up, are pending operations. These are known as pending operations, right? And essentially they're waiting to be evaluated, and they build up. Okay. Now, so the thing is that, like physicists, for us in computer science, we care about two things. What are two things? Time and space, very good. Okay, so time is how long it takes for a program to run. Okay, it turns out that programs don't run randomly; they actually need memory. Okay, so we also need to know space. We need to know how much memory it takes to run the program. Okay, back to this example. Okay, the time is obviously proportional to how many operations it takes to open up and close. Okay. And obviously, if you look at this thing, you will see that it's something in the order of 2n minus 1, right? So the amount of time taken is linearly proportional to n. Okay. Now, it turns out that the number of pending operations, okay, the pending operations, all the tricks take up space in memory. Okay, so the space is actually proportional to the number of pending operations. Okay, so this one takes about n minus 1 stars. Okay, so it's also linearly proportional to n. Okay, so what is recursion? Recursion at a high level is the following. You have the problem that's of size n. Okay, typically what you do is that you express the problem of size n as a problem of size n minus 1. Okay, and then subsequently you keep going down at some point until you reach some point. Okay, whereby it's very simple. This is known as the terminating condition. And then once you terminate, the answer is completely trivial. You just write the answer, okay? And then what happens is that you will just close, okay? And you will just kind of essentially open up, and then you close up, okay? And this gives you the final answer. Okay, so recursion has two basic steps. The first thing you do is that you must go and figure out what is the base case. Okay, typically you will deal with something simple like n is 0, n is 1. Okay, and the next thing you do is this: you go and figure out the following. You assume that you know how to solve the problem for n minus 1. You ask yourself, how do I solve this problem for n? Okay, and you express n in terms of n minus 1. Okay, so in this example for factorial, okay, you have the codes above, and then you have this thing whereby factorial 4 is dependent on factorial 3, is dependent on factorial 2, and so forth. And then factorial 1, you actually know the answer to it just by you can spot the answer, and it's done. So for any n, what happens is that the computation will go all the way down to 1. When it's 1, it will terminate and return 1, and then after that, it will just close up all the way up to the top again. Okay, this particular process is known as, okay, linear recursion. All right. Okay, next you have this very famous guy called Fibonacci. Okay, he created this. You can't count this numbers called the Fibonacci series, right? So it's this thing whereby each number is the sum of the previous two numbers. Okay. And mathematically, you can express the Fibonacci sequence in the following way: f0 is 0, f1 is 1, Fn is the sum of Fn minus 1 and Fn minus 2. So this is the Fibonacci numbers. Okay. Now, obviously, okay, so this is the definition. It turns out in the scheme, it's completely trivial to do this, right? You can do what? A con, right? Because now there are three, okay, if you only have two cases, A or B, you use the if. Now you have actually three cases. So use a con. So con is that if n is 0, return 0. If n is 1, return 1. Otherwise you return what? Else you return n minus 1 and n minus 2. So if you look at upstairs and downstairs, I mean the top is actually the mathematical definition of Fibonacci. Okay, the bottom is actually the scheme definition of Fib. Okay, and the two, frankly, are the same thing. Okay, are we all clear? Simple. It turns out it works. Okay, now if you look at how, okay, just now we showed you how the recursion works, right? Now if you look at Fibonacci, okay, it turns out that what happens is that to compute Fib 5, you need to compute Fib 4 and Fib 3. Okay, to compute Fib 4, you need to compute Fib 3, Fib 2. And then if you open up all these operations, right, you will look like this, right? Okay, and we call this tree recursion because it looks like a tree, right? And then these things, we call them leaves. Okay, the endpoints are called leaves. And this first thing is known as the root of the tree. Okay? So, it turns out the number of, okay, so the thing is that we care about how much space and how long it takes, right? Okay? So obviously, in order to compute this number, you need to traverse the whole tree. So, obviously it takes as long as it takes to go and get the leaves, right? So the question is, how many leaves are there in the tree? It turns out that the number of leaves in the tree is exactly Fib n plus 1. Okay, it turns out this is true. And it can be shown mathematically that Fib of n is actually the closest integer to phi n divided by the square root of 5. It turns out this phi is actually this number, which is 1.618, which is root 1 plus root 5 over 2, which is apparently the Mona Lisa, apparently, the height of Mona Lisa divided by the width of Mona Lisa's face. And apparently, if you have that kind of ratio, you look handsome or pretty. Okay, so next time you're going to go see, some cosmetic surgeon or something, you check whether or not he gets his golden ratio correct. Okay, if you already have it, good for you. Alright, so anyway, the time taken is therefore phi n. Okay, and so because the number of leaves is phi n, okay, that's why we know that it will take about phi to the n time to compute, and so this thing will take exponential in n in time. Okay, then the question now is, okay, this is the exponential in time. Now, it turns out that the space required is proportional to the depth of the tree. Essentially, if you go through the process, you realize that you need to keep as many pending operations as the depth of the tree. The tree depth is how deep? Linear, it's very linear. So basically, this tree recursion will take exponential time, but linear space. Okay. Then you have another kind of recursion, which is called mutual recursion. Okay, we look at this silly example. There's this thing called ping and this thing called pong. Okay. Now, basically, for both of them, if n is 0, you return n. Okay. Otherwise, you display ping or pong, and you call the other guy. So ping calls pong and pong calls ping. Alright. So if you run this code, you will get the following. You get this ping. You're supposed to do ping 10. You do ping pong, ping pong, ping pong until it ends. Okay. So this thing whereby two procedures will call each other, okay, is known as mutual recursion. Okay. In fact, actually RSM. Okay. Some of you don't know because you missed the Saturday lecture. So RSM is not regimental subject major. It's not the guy who shouts commands. It's